So it is recording now. Yes. Okay. First question, we have a piston that compresses a gas in a cylinder by moving at constant speed v. As in the figure, let the gas density and length at t equal to 0 be rho 0 and L0 respectively. Let the gas velocity vary linearly from u is equal to v at the piston face to u equal to 0 at x equal to L. If the gas density varies only with time, find an expression for rho of t. Okay, this was a question in my midterm, in my final. It's also the same question as 9.1 example in the book. Okay, but this version I think it's somehow better, and it doesn't give you the equations directly. It wants you to derive the equations. The velocity is in the same direction, or the velocity of the gas is in the same direction of the compression, and it makes sense because when we push the piston from here, you expect the gas to move to the right. Yeah, بس الفيرجن تاع البوك I think they put the velocity of the gas downward and the compression is upward. Okay, maybe there is something regarding the gas that's being compressed, or how the process is done, but this one it's more logical for me. Okay, so how can we solve this equation? It's clearly we can do it by using continuity, صح? لأنه we have the velocity, we have everything. The only thing that's missing is the density, but we should use the continuity equation for the compressible flow, okay? Because the density is changing. So we cannot use the continuity equation for the incompressible flow, okay? What's the continuity equation for the compressible flow? It is in the differential form, of course, because chapter 9 is about fluid using the differential analysis, okay? Not the integral analysis. So partial, okay, rho by partial t plus partial u, okay, rho u, don't get the rho outside, by partial x plus partial rho partial, okay, v over y plus partial rho w by partial z should be equal to 0. This is the continuity equation for the compressible flow. Okay, this is the first step. And now after you write the equation correctly, you can continue. طيب. What else can we do? We can observe we only have velocity in the u, صح? Or in the x direction. So we have only this velocity component. There is no velocity here, okay, so it is 0, and there is no velocity here, so it is also 0. Okay, لأن واضح صح؟ طيب, partial rho by partial t, okay, is equal to minus, okay, partial rho u by partial x. We can get this rho outside. Why? Because في question he says that the gas density varies only with time. So the density is only a function of time and nothing else. Okay? The density is a function of the time and nothing else. It's not a function of space. Here, the density will be the same. But as the time goes by, okay, the density will be changing due to the compression. So the density is not a function of space, it's only a function of time. So we can get the density outside. So partial rho by partial t. نعم.
Since it changes with x, shouldn't it be 0? Because as you said, it doesn't change with the position.
It doesn't change with the position, it changes with time. So I can get rho outside.
But it doesn't become 0. Doesn't become as 0 when changes with x.
كيف 0 No, the density is not 0.
هو انت doesn't change with x. لكن what's that? موجود change with x صح؟
Okay, we want to find the change of density with time. Okay.
Okay, so the change with x, is it 0?
Yeah, there's no change with x. Yeah, so we can get the rho outside. rho بالنسبة للx هي constant, so we can get it outside the derivative.
Okay.
If we have maybe مثلا partial by partial x مثلا of 5yx. Okay, 5y is constant, so we can get it outside the derivative. Okay, and then differentiate with respect to x for x only. Yes, because 5y with respect to x is a constant. Okay, rho with respect to x is a constant, so we can get it outside the derivative. You get it?
Yeah, it doesn't change. Stay the same. Okay.
Okay. So, okay, let's continue. So our rho is now outside equal to minus rho partial u by partial x. Okay, so what's left for us is to write an expression for u, okay, with respect to x, because we only know u, but we don't know its expression with relation to x, okay? So we need to write the expression for u, okay, before we start solving. How can we do the expression for u? Okay, we have some boundary conditions that he tell us, okay, u at here is equal to kada, u at here is equal to kada, so we can calculate them. For example, 9.1, it's given for you. It's given for you the equation of u directly. But here we can derive it from the conditions. How can we do that? شوف هنا ركزوا كويس في المعلومة اللي مكتوبة هنا. The velocity varies linearly, okay? So u is a linear function. Okay, and then it starts from where? It starts from u is equal to v, okay, at the piston face to u is equal to 0. U is equal to 0. Okay, u is equal to v where? And u is equal to 0 where? U is equal to 0 at x equal to L. And at x equal to 0, u is v. So how can we derive the linear function for this? Okay, u is a linear function. Linear function is mx plus b. صح? The linear function is mx plus b. So we need to get the slope and the intercept, أو يعني اللي هي initial condition. Okay. So at 0, at x equal to 0, u is v. So this is it. So b is equal to v. ليه؟ لأنه لما نعوض 0, okay, this will cancels, and then u is equal to v. So b must be v. Okay. And then when u is equal to 0, now, when u is equal to 0, which is now 0, equal to mx plus v. Okay, v is the velocity of the piston compression. Okay, the velocity of the piston compression is constant, but the velocity of the gas inside is not constant. Okay, it's a function that varies linearly. Okay, so now 0 equal to mx plus b. What is m? Now, m, it's going to be minus v, okay, at where? At L. So I should substitute x by L. Okay, minus v over L. Okay, that's m. So now I have the expression for the velocity. The velocity equal to minus v over L, okay, x plus v. Okay, this is the expression for u. So now let's substitute partial rho by partial t equal to minus rho partial u by partial x. Derive u with respect to x. What you will get? You will get minus v over L. صح ولا لا? v over minus v over L, x plus v. This is a constant, and this is the derivative. Here we have x to the power 1, so it will goes, and then we will have only minus v over L. Okay, لحد هسه clear ولا لا؟ clear. Okay, تمام. Okay, we can take the minus with the minus, and then we have this. So now we are left with a separable differential equation. Okay, why is this a separable differential equation? Here we have okay, I forgot to change this partial derivative to exact derivative because the rho is only a function of time. Okay, so we can change this to exact derivative, because the rho is only a function of time. طيب, now this separable differential equation, I can divide by rho, okay, and multiply by dt. So when I divide by rho, okay, and multiply by dt, this is what I am left with. Okay, now I need to integrate both sides, but remember, this is the v capital, which is the compression velocity, which is constant, but L changes with time. How does L change with time? Here, كمان في question. He said that let the gas density and length at t equal to 0 be rho 0 and L 0 respectively. Okay, so here, okay, here L is L 0. Okay, and here L is different. So L is a function of time. Okay, the position, okay, of the piston is a function of time. Now, again, I need to get an expression for the position of the piston, okay, that includes time, okay? How can I do that? Same, using the same boundary conditions, okay? Now, my L, okay, equal to L node, where at here, okay, at time equal to 0. So L equal to L naught, which is this is the B, okay, same as there, L naught. And it then decreases, but remember that L decreases with time, okay? So if I move there, the L will decrease. So it is minus the compression velocity multiplied by time, okay? When the compression
Mahdi,
velocity, because, نعم, okay.
please can you repeat this part of the L again?
تمام. الفيرست بارت مفهوم صح، اللي هو how we get the
Yeah, till
velocity
we got the
equation صح؟
equation. Yeah, till we got the
Okay.
equation and we do the row, it was okay.
Okay. تمام. So let me repeat it. So now we have some boundary conditions for the L equation, okay? Now we know that L is equal to L naught at time equal to 0. And we know that the piston moves with a constant speed, okay? The piston moves with a constant speed. صح ولا لا? The piston moves with a constant speed.
Given?
Okay.
It's given already. It's
No,
written, yani.
constant. V is equal to constant. The
Okay.
piston movement, not the velocity of the gas, the piston movement. Okay, the piston movement is constant. What is the distance that the piston will travel? It is V multiplied by T, صح؟ المسافة بتساوي السرعة ضرب الزمن، صح؟ المسافة بتساوي السرعة ضرب الزمن، ليه؟ لأنه يعني حركة بسرعة ثابتة. Okay, V multiplied by T. Okay, so L naught minus VT. Why is that? Because here at the beginning we have L naught. And as the piston moves, okay, we are decreasing. The L naught is decreasing, okay? So yani we assume that the L here at the beginning is L naught, okay? يعني إنه L, this is L naught, okay? The distance at the beginning, okay, that the gas is enclosed in. And then as the piston moves with constant velocity, okay, the piston moves with constant velocity, now this L naught will decrease. What is the factor of the decreasing of L naught? It is Vt, yeah, the distance that the piston travels. So L naught minus Vt, this equation represents the length, yeah? Let's say that we have time 0 to check if we satisfy the boundary conditions. At time 0, L will equal to L naught, okay? And let's say at the time where this one is closed, okay? يعني, which is maybe, let's say T final, okay? So L naught will be equal to Vt, and then L will be 0, okay? So L represents the distance which the gas is now enclosed in, okay? L naught represents the maximum distance or the distance at the beginning, and Vt is the decreasing factor of the distance that's enclosed inside the piston, okay? مفهوم ولا لا؟ طيب اوكي again this is the piston. مفهوم خلاص تمام. Okay, so now this is the equation of L, which is L naught minus Vt. Okay, now we can integrate both sides. Okay, so integrate dp over rho from rho naught, because he told me no, rho naught is the rho at the beginning, to rho as a function of time, which we want to find, equal to the integral from 0, the initial time, to the final time, which is, let's call it t, okay, of dt, okay, okay, 1 minute, of v over L naught minus v t dt. What's the integrals? Lens, صح? So it is ln rho from rho t to rho naught equal to, here minus ln, we have minus ln لأنه هنا في minus, okay, ln L naught minus VT, okay, from 0 to T. Okay.
مهدي
نعم.
ال V مش constant، ليش ما نطلعها برا الانتجرال؟
Okay, we can do that، بس انه نحن عايزين نستفيد من انه الانتجرال هو لن.
اوكي
صح؟
فهمت.
فانه اذا طلعتها you have to multiply by V again.
صح.
طيب اوكي، تعال نعوض. اللن تاع الطرح بتحول لقسمه، صح؟ يعني لن رو تي ماينس لن رو نوت بتحول لن رو اوفر لن رو نوت، صح؟ يعني لن رو minus ln rho naught equal here to minus ln L naught minus VT plus لأنه هنا في outside minus plus ln اللي هو لما when time is 0 it will be ln L naught. So here we have a division ln وهنا we have كمان a division ln because this is the minus and this is the plus. Okay. لأنه we need يعني at the end to get rid of the lens. We want a function of rho, okay, as يعني إنه function of rho t, okay, with the other variables, okay. So let's do the division rule. It is ln of rho t على rho naught بيساوي, okay, this is the positive one, so the positive one is up, ln L naught over L naught minus Vt. We can get rid of the lens together, صح? So now we have rho as a function of time equal to rho naught L naught over L naught minus Vt. Okay, this is the function. We can do يعني a small tweak, okay? إذا عايزين نسوي لها non-dimensionalize, what we can do is that rho t, okay, over rho naught نقسم على rho naught, and this will be the dimensionless rho, okay? And we can also say that V t over L naught is the dimensionless time, okay? Because V over L is the reciprocal of the time, okay? And then time over time will be time dimensionless, okay? Same as rho over rho. So now we know that rho is equal to or low dimensionless. Here we got L as a common factor and L as a common factor, so it will cancels. يعني هنا L, and here we get L as a common factor. So this will be 1, here divided by L naught, okay? So now we have 1 over 1 minus dimensionless time. Okay, يعني no need to get this form, but يعني this one will help you if you have an experiment now. يعني مثلا if I give you data, أو ممكن البروفيسور give you data, مثلا now you at مثلا here at several points. مثلا at the first point rho is كذا, okay, the time is 0, L naught is equal to the velocity is equal, and then here مثلا at x equal to 4 مثلا now the velocity is equal, now the rho is equal, and you know to يعني you want at the end to مثلا measure how is rho changing. So يعني it's not إنه convenient to measure the change of rho with all these variables. So it is better now يعني if we have a plot of rho dimensionless with time dimensionless, okay, and we can يعني see how they are changing together. Maybe you have a function like this, a function like this, whatever, and يعني that's it. Okay, فاهمين كويس؟ عايد أي point؟
طب مهدي انت الايكويشن اللي بدات فيها هي الكونتينيوتي ايكويشن للكمبرسبل فلو؟
equation لا للcompressible flow. yes.
طب ولما تكون انكمبرسبل اللي هي نفسها
نفسها بس
رو في
انه
ايه؟
الروز out يعني this one will be 0, okay, all the rows now will be outside, divide them over the 0, you will get 0, so you now have only partial u by partial x plus partial v by partial y plus partial w by partial z. This is for the incompressible flow. Okay.
طب معلش هي ايش الفرق بينه وبين الرو في ايه اللي كنا نستخدمها في الفلويد؟
رو في a
الكونتينيوتي ايكويشن
كيف يعني؟ ما فاهم عليك. رو في a
مش كنا نستخدم في الفلويد الكونتينيوتي ايكويشن اللي هي رو في ايه؟
كنا نقول في الفلويد الكونتينيوتي equation
V1 V2 V2 A2 لما يكون 1 inlet 1
يعني
outlet.
قصدك A V1 is equal to AV2.
ايوه
This one. Yes. Okay. But this one in the يعني this is the general formula. The formula
differential form.
use بالضبط differential form for it.
تمام.
Okay. Yeah. So yes.
We have to follow this process always from start to the end يعني.
يعني maybe now because you have multiple choice questions, so maybe you don't have a question like this. Okay. بس إنه بشكل عام if you have a question, at first you have to put your assumptions. What is the flow? Is it steady? Is it not steady? Is it compressible? Incompressible كده. So you know what equation you will use, and then see what things you have, what things you don't have, and then calculate for the unknowns. This is the always the process that you will go through. Okay. طبعا now it's very easy
compressible هي صح؟
this one for the compressible flow. Okay. now it's easy because it's only the continuity equation. بعدين you will use the Navier-Stokes equation, and you will have a problem, and the problem have boundary conditions, and then you need to get the C and the C2. Okay. نفس اللي تقريبا أخذتوه في الheat chapter 2. Same thing. You have the equation of the heat, Poisson's equation, and you need to get C1, C2, C3, any constants having when you have the boundary conditions. Okay. But now it's easy. You either have the velocities, you now need to calculate the density, or you maybe have two velocity components, you need to calculate the third velocity component, but you don't have مثلا two velocity components that are not given. If you have two velocity components that are not given, you have to solve using the Navier-Stokes equation. Okay. Because the Navier-Stokes equations are three sets of equations in the x and in the y and in the z, and with the continuity equation now you have four equations. Okay. So you can solve for the velocity in the x, the velocity in the y, the velocity in the z, and the pressure field. Okay. The velocity fields or the pressure fields. بعدين الموضوع ده إنه بتاخدوا part 2 of chapter 9. Now we are in part 1. Okay. So yes, this is question 1. Okay, let me erase. Okay. Question 2. No. Okay. So, question 2. This is from Monson book. Okay, the first question was from Frank White book. Okay, the stream function for an incompressible. Okay, you took the stream function. Stream function is a function defined by Lagrange, so that it has velocity components both in one function. Okay, this is the stream function. Okay, and it have to be a smooth function of x and y. Professor Khad explained that in the theory. But when you solve, okay, there is two important things when you have the stream function. Okay, either he is going to ask you for the volumetric flow rate, okay, which is one of the physical significances of the stream function, okay, that the stream function, okay, مثلا at 2 مثلا minus the stream function at 1 equal the volume flow rate per width. Okay. And the stream function, the value of the stream function is going to be higher on the left side of the flow. Okay, so maybe I have this one. Okay, this is stream 1 and this is stream 2, and I have a flow here. Okay, so the value of psi 1 and the value of psi 2 should be higher than psi 1. Okay, because the flow is going in this direction, and then the stream value on the left side of the flow should be higher. That's in the theory, but in solving problems, what we have, either he asks you for the volume flow rate, okay, so psi 2 minus psi 1, or maybe he asks you for one of the velocity components. So we have some definitions how the stream function is defined with velocity components. So maybe for two-dimensional flow, okay, we know that u is equal to partial psi by partial y, and v is partial psi by partial x, but with a negative sign. Okay, this is 2D flow in the Cartesian coordinates. So maybe in other coordinates like the cylindrical coordinates, we can have, okay, 1 minute, let me erase. Okay, yes, so maybe in 2D cylindrical coordinates, we know ur will be equal to 1 over r, partial psi by partial theta, okay, and u theta will be equal to minus partial psi by partial r, okay. And for axisymmetric flow also, this is yani cylindrical coordinates, so like that the flow is like that, it's polar, okay. And the axisymmetric cylindrical is like this, okay. So yani we are seeing the cylinder from the side. This is the axisymmetric flow, okay. In this direction, okay, maybe the flow, or in this direction. This is the radial, and this is the z, okay. And yeah, so that's it. So let's look at our question. It asks us for doing the two things actually، يعني انه الطريقتين الاسئله موجودين في نفس السؤال. طيب the stream function for an incompressible flow field is given by this equation. So this is the stream function, where the stream function has a units of meters squared per second, okay, and x and y in meters, okay. So يعني it's no normal أو يعني understandable, because إنه the stream function per unit width is going to give us the volumetric flow rate, okay. So it's meter squared per second. Sketch the streamlines passing through the origin and determine the rate of flow across the straight path. Okay. Part A تقريبا يعني هو من الفلويد ميكانكس مش حتى من الادفانس فلويد. How can we sketch the streamlines? Actually, the stream function, okay, يعني same equation as the equation of the streamlines, but we need to separate it يعني x equal or y equal. Okay, so I'm going to do that. Which one is easier here? X equal or y equal? To separate it. X equal صح، لأنه هنا في x في one term only, so we can take the y to the other side and divide by y. Or if you take it as y equal, also it's the same, بس إنه x equal is easier. طيب 3x square y equal to psi minus y plus y cubed, and then divided by 3y. So now we have x squared equal to psi plus y cubed over 3y, and then we get rid of the square by doing the square root, okay. So this is the equation of the streamline. He wants me to sketch the streamlines that pass through the origin. What's the origin? The origin is x equal to 0, y equal to 0. How can I implement that here? Okay, so when I have x equal to 0, okay, I need the other side also to be equal to 0. Yes, this side. Okay, and y is also equal to 0. طيب عشان إذا في عندي كسر، okay، والكسر لازم يكون قيمته صفر، فمعناها المقام البسط على الكسر لازم يكون 0 صح؟ The numerator of the fraction should be 0. Yes. So 0 is equal to the square root of psi plus y cubed. Okay, and we know that y is equal to 0. So psi is 0. Okay, for sketching the streamlines that pass through the origin, psi should be 0. Okay, so let's write the equation of the streamlines that pass the origin. Okay, so here is 0. Now we know that x is equal to y cubed over 3y, which is also equal to, let's get rid of this, and here we have a squared, and then we have, you know, the square root of y squared, which is going to be y plus minus, okay, don't forget the plus minus, over the square root of 3. Okay, so this is our equations of the streamlines that pass through the origin. Let's sketch them, okay. يعني let me sketch them below, so we have some area and you can see the sketch clearly. Okay, what's x equal to y over the square root of 3? Okay, let me write it as y equal, because you are used to write functions when y equal. Okay, y equal to square root of 3x. This is the first function. Second function, y equal to minus square root of 3x. So one of them is going to be like this. One of them is going to be like this. Okay, not very clear. Like this past the origin. Okay, and the slope is going to be square root of 3 here minus square root of 3. Okay, so these are the streamlines that pass through the origin. Okay, very easy يعني، بس إنه check how can I satisfy that the streamlines pass through the origin. I need to get x alone or y alone to write the stream function. Okay, it's easier here in this example to get x alone, and then see what value of psi will give you the sketch to pass through the origin. Okay, to be 0, we need here, okay, the numerator, okay, or the denominator, okay, to be equal to 0. So psi should be 0 because y is 0 and x is 0. Okay. Now the second part of the question, determine the rate of flow across the straight path AB shown. So I need to know the flow rate, okay, the volumetric flow rate, okay, going from A to B. So the volumetric flow rate going from A to B per unit width, okay, is equal to psi B minus psi A. Okay, this is the physical significance of the stream function. What's psi B? Substitute. Okay, substitute. Here, this is point B. 1, 0. So 3 multiplied by 1. Sorry, 3 multiplied by 0, and here 1. Okay, so this will be 0. And here minus y cubed, so minus 1 cubed. It's going to be minus 1. And then psi A, here, this is the point A, 1, 0. So substitute y as 0, here 0, here 0. So it's going to be 0, minus 0. So it is minus 1 meter squared per second. This is the volumetric flow rate per unit width. If he gives you like the width now is 3 or the width now is 4, multiply by the width and you are going to get the actual volumetric flow rate. Okay, understandable؟ يعني مش عارف easy يعني ما اعتقد في شيء يعني بس انه اذا في اي شيء قولوا لي. You get it guys?
Yes. Okay.
تمام. دخلت من الاول خالد ولا؟
أول السؤال الأول ما لحقت أول دقيقتين منه
بس الثاني انا شفته يعني كويس.
أيوة.
اوكي تمام. بس
Mahdi,
yes.
I think the lesson more focuses on the example of the first one, صح؟ هي الفكرة الأساسية.
الفيرست one is about the continuity equation. Second one is about the stream functions. Okay, so you now took يعني two things, continuity equation وال stream functions, part 1 of the chapter.
Okay, في other parts في same chapter.
في part 2 اللي هو Navier-Stokes equation و solving questions with boundary conditions. That one is harder. That one for
هذا كله chapter 9. Okay.
كله
okay.
chapter 9 بس يعني we finished now بس part 1. Okay. So
Okay.
I think يعني we finished اللي هو two problems اللي here. كم ساعة؟ يعني في لسه في وقت. Let's solve these questions. Okay, these are questions from Jingle book. Okay, so how can I do that? Okay, let me close the share and let me open here. Yeah, Jingle's book. Okay, and how can I share the screen again? Share the desktop. Okay. Okay. So this is the first problem that we need to solve from Jingle's book. Okay, consider, and these are easier problems, okay? Consider the following steady three-dimensional velocity field in the Cartesian coordinates, which is V equal to U, V and W equal to, this is the velocity field, okay? So where A and B and C and D are constants. Under what conditions is this flow field incompressible? Okay, these are usually يعني او ده هو طبع الكويستشنز اللي بيجي في المالتيبل تشويس يعني غالبا يعني هتشوف كتير منهم اذا كان في عندك ميد تيرم او يمكن حتى في كويز. ف how can we solve these؟ يعني simple derivatives quickly you can get the relation بعدين you plug it in. Okay, so what is the relation or what's the condition that will make this flow field incompressible? We discussed it في الأول question. Okay, for the flow to be compressible, the continuity equation for for the flow to be incompressible, the continuity equation for incompressible flow is partial u by partial x plus partial v by partial y plus partial w by partial z equal to 0. If this is satisfied, then the flow is incompressible directly. Incompressible. Okay, it is gradient dot v. Okay, gradient dot v equal to 0. The flow is incompressible. This is the compressibility equation, or sorry, the continuity equation for incompressible flow. So let's check it and see at which conditions or at which values of these constants this equation will be satisfied. So just apply the equation on the velocity field that you have. Partial v by partial u by partial x is going to be a y squared, yes? So now we have partial u by partial x is equal to a y squared. So, and then partial v by partial x by partial y is equal to partial v by partial y is equal to minus 6, okay, cy, yes? Sorry, minus 6 cy squared. So minus 6 cy squared. And then partial w by partial z equal to 0. صح؟ لأنه there is no z in the z component of the velocity. صح? So the partial by partial z is equal to 0. Okay? So now we end up with only these two. When is this flow incompressible? When partial u by partial x equal to minus نقول على الطرف الثاني partial v by partial y. طيب.
You started deriving or you just took the values?
لا I derived. أنا مسكت velocity field. هنا velocity field. Okay, this is the velocity.
Okay.
axy squared minus b. This is the x component, and this is the y component, and this is the z component. So derive each component with respect to the length in that direction. So with respect to x, with respect to y, with respect to z. Add them together, they should give you 0. Why? if يعني احنا مش عارفين اذا الفلو incompressible ولا لا. فيعني اول شيء بتفترض انه incompressible، بتطبق معادله الانكمبرسبل فلو، الكونتينيوتي في الانكمبرسبل فلو. اذا طلعت صح معناها your assumption is correct. This flow is incompressible. طب اذا طلعت غلط يعني معناها no. This flow can be compressible or can be anything else. Okay. So now if our flow is incompressible, this should be true. Okay. طبعا لما ننقل على الطرف الثاني حيختفي السالب لانه سالب موجب. ف c y squared, cancel y squared with y squared. So our condition should be a equal to 6c. If it is incompressible, okay, which is the answer here. Under what condition is this flow incompressible? A equal to 6c. Okay, and these questions are nothing بس انت على طول تشوف okay what does he want. So if the flow is compressible maybe, so apply the compressibility equation, apply the continuity equation for compressible flow. Okay, maybe if the flow بعدين في chapter 10 if the flow is rotational, how can we know rotational flow? أخذتوها في الفلويد. It's grading cross V. Okay, that's the how to know if it's rotational or not. If it's equal to 0, then it's irrotational, and if it's not equal to 0, then it's rotational. Okay, and many things like that. It gives you the velocity field, and you see maybe if we want to see if the velocity is or the flow is steady or no, how can we know? معناها partial rho by partial t should be equal to 0, and partial v by partial t should be equal to 0. The derivative of all the velocity components in the time with time is 0, and the derivative of the density with time is equal to 0. So the flow is steady. Okay. Maybe the unsteadiness come from the energy equation, okay, from temperatures and these things. بس إنه في fluid mechanics you don't now deal with the energy equation for now. If you don't see any time in the velocity equation or in the velocity field, okay, the flow is steady. Once we had a question in the midterm, let me write for you our question. He gives us a velocity field, and he says 1 plus 2xi plus 1 minus 2yj. Okay, this is the velocity field that he gave us in the midterm, and he told us, according to this velocity field, is the flow compressible, incompressible, steady, unsteady, or both B and C together? Okay, both B and C. Okay. So first, apply the continuity equation for incompressible flow to see if it's compressible or no. Apply it. Partial U by partial X plus partial V by partial Y equal to, what's partial U by partial X? It is 2, صح? 2. And then plus, what is partial V by partial Y? Minus 2. So it is equal to 0. So the flow is incompressible. Now check for steadiness. Partial U by partial T plus partial V by partial T is equal to, في any time هنا في الإيكويشن كلها في time ما في time خلاص 0. So the flow is also steady. So both this and this. في البداية البروفيسور يعني كان إنه بيقول إنه this equation, the compressibility equation or the continuity equation only determines for you if the flow is compressible or incompressible. So يعني he used to إنه يعتمد الحل ده. Okay, إنه incompressible only. But if you don't have time in the equation, so partial V by partial T is also 0. Okay, يعني بعدين I told him about it and he told me إنه yes. So بعدين هو اعتمد الحلين. Okay, إنه it should be incompressible and steady. تمام؟ حتى لو unsteadiness ممكن it's coming from the energy equation, but he gives you the velocity as it, you see it, there is no time in the velocity equation, خلاص, it's steady. Then check, incompressible. Okay, you applied the continuity equation for the incompressible flow. Correct? Also incompressible. Not correct? Then the flow is compressible. So it is steady and compressible. Okay? Clear؟ يعني ما في شيء يعني بس انه check يعني your states. بعدين في كمان اللي هو انه الفورتيسيتي عشان تتاكد اذا الفلو روتيشن ولا لا chapter 10 كمان maybe you can check if it's rotation or irrotational. Okay. I think انه الاشياء دي مرت عليكم كمان حتى في الاناليتيكال maybe. تمام. طيب السؤال اللي بعده what is it? Yes, we have question 955. Okay. Question 955 says that question 955 in Jingle's book. 955. Yes, there are numerous occasions. Okay, يعني blah 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 للآخر. Okay, we now have the psi. Okay, so generate an expression for the radial and the tangential velocities. Okay, this is at cylindrical coordinates. Okay, because we have theta and يعني x and y. Maybe you can call them radial, which is r, and here inside يعني you can call it z, whatever. المهم إنه this is the psi, okay, which is the stream function. Generate two expressions, radial and tangential velocities. سهلة بس نطبق القوانين اللي موجودة عندنا for the velocities in cylindrical coordinates from the stream function. بس يعني derivative, partial derivative only. So partial derivative of psi by the partial theta, okay, multiplied by 1 over r will give me the velocity component in the r, and the velocity component in the theta is minus psi, okay, over partial r. Okay, these يعني انه equations I don't know if they should be given. اتوقع امتحانكم open book, so يعني you go. Okay, وين موجودين هم؟ here. Okay. The stream function equations. Okay, موجودين هنا. Stream function equations for 2D incompressible Cartesian coordinates. This is it. You may be asked to calculate U from the stream function or V from the stream function. 2D incompressible cylindrical coordinates. U, okay, here, and U theta here. Axisymmetric incompressible cylindrical coordinates, okay? Axisymmetric, this is it. This is the equation for the axisymmetric flow. And 2D compressible Cartesian coordinates. This is it, okay? For the compressible. Look, في رو هنا. So which case we have? We have this case. Okay? The 2D cylindrical coordinates. الفرق بين axisymmetric و cylindrical إنه normal cylindrical like this. Okay, you have theta and you have r radial. Axisymmetric, it's like this. Okay, you have the radial here and you have the z here. Okay, theta يعني it's not shown هنا. أما هنا z is not shown. This is the difference. This is the axisymmetric cylindrical, and this is the normal 2D cylindrical. Okay. So we use the first set of equations, صح? For the 2D cylindrical coordinates, and because you saw the question. So let's write down them, and to not forget them. UR, the expression for UR is going to be 1 over R, partial psi by partial theta, and the expression for the U theta is going to be minus partial psi by partial R. Okay? So let's just check our stream function for this question. This is it. Psi is equal to V sine theta R minus A square over R. So psi is equal to, oh, I forgot it, V sine theta multiplied by R minus A square over R. R minus A squared over R. This is the equation. Just let me check it again. Yes. So first one, UR أول شيء derive with respect to theta. So partial psi by partial theta is equal to, there's no negative, so derive directly. V, the only theta here is with the sine. What's the derivative of the sine theta? Cosine theta. And then all of these are constants. Okay, they will stay the same. Yes. And now multiply by 1 over R. So UR is equal to multiply by 1 over R, صح؟ اوكي ممكن احنا نحذفهم من هنا على طول. كوساين نحذفها هتكون 1 ماينس هنا لما تضرب هتكون R squared.
Why do you multiply by 1 over R?
We want to get the expression for the velocity in the radial direction. ده هو السؤال يعني انه get the velocity in the radial and in the tangential. Okay, the radial direction which is UR, the tangential direction which is the theta direction. Okay, we are now in cylindrical coordinates. Yeah, I'm sorry, maybe some of you are not familiar with cylindrical coordinates. Yeah, maybe they didn't took it in the analytical. يمكن خالد كده يعني. This is the cylindrical coordinates. Okay, this is the theta direction. Okay, which is the tangential, and this is the radial direction here. Okay, here this is the radial direction here, like this radial direction. Okay, so it's almost like يعني polar coordinates. Okay, polar coordinates. صح? What you have in polar coordinates, you have R and theta. صح? Polar coordinates in calculus 2. R and theta. So this is it. يعني we need to get the expression for the velocity in the radial direction and in the tangential direction. Don't complicate things يعني just equation يعني على طول. بس هنا نفتح وريتكم في الصفحة بتاعت الكتاب عندنا القوانين اللي بتربط الستريم function with the velocity. Directly apply them. بدون تفكير يعني على طول. Directly apply them. Okay. Partial psi by partial theta. We got it. And then multiply by 1 over R. لأنه القانون يعني فيه كده بس 1 over R تضرب فيه. فاضرب في 1 over R. لما نضرب في 1 over R الR هنا هتروح هتكون 1 وهنا هتكون إنه R squared. بس this is the expression for UR. Done. بعدين U theta equal to, we need to derive with respect to R and then multiply by the negative. So derive this equation, the stream equation with respect to R. This R will be gone, it will be 1. And for this one, what's the derivative of 1 over R? It is minus 1 over R square, صح? The derivative of 1 over R. So it is going to be V sine theta, and هنا ما له علاقة, multiplied by, this is going to be 1, okay? And this is going to be negative, هنا في already negative, صح? So it's going to be positive A square over R square. This is the expression for the theta. Oh, sorry, I forgot to multiply by negative outside. So this is it. This is the radial velocity, this is tangential velocity. بس يعني we have two type of problems. Either we have the velocity components, okay, U and UR and U theta, okay, and he tells me like get the expression for psi, okay, or I have psi and I need to get the expressions for the velocities. psi to the velocities is easier, and I just do derivatives. But from u to the psi, I need to integrate. Okay, and maybe let's reverse the question. We need to get psi. Okay, so how can I get psi? This is ur. Okay, ur, I need to multiply ur by r and then integrate it with respect to theta. So multiply ur by r, what we will have? We will have cosine v, cosine theta r minus a squared. When we multiply, we will have r, okay? And now this one integrated with respect to what? With respect to theta, صح? Here. And we multiply by r, okay? And then we integrate with respect to theta. So what will be the integral with respect to theta? What's the integral of cosine theta? These all are constant. What's the integral of cosine? Integral of cosine.
Minus sine.
Sine.
Okay. So integral of cosine is sine theta r minus a square over r, and don't forget plus a function of what? Yani now we integrated with respect to theta, so plus a function of r. Okay, a function of r. Yeah. So now this is psi. Okay, how can we get this function of r? Now we have the second expression. Derive with respect to r and multiply by negative. If we derived psi with respect to r and multiply by negative, okay, it's going to be equal to v sine, okay, طبعا multiply by negative, r will be gone, so it's 1 minus here الماينس مع الماينس هتكون positive, a r square, okay, plus f prime of r. طيب, how can we get this f prime? ساوي, this is u theta, صح? ساوي u theta في all this expression and get the unknown. So u theta was minus v sine theta 1 plus, صح؟ اللي هي exactly this thing. صح? So what is the function of r? The function of r is 0 now. The derivative of the function of r. So f prime of r is equal to 0. Okay. So what is f of r? F of r will be a c, a constant. Doesn't matter, يعني whatever you put this constant, but يعني this is the يعني formula that you have. Okay. سهلة؟ ما أعتقد فيها شيء يعني either from here to here or from there to there بس. Okay. في شوية دقائق نحل كمان سؤال. سؤال 9:36. حتى أسهل منهم كلهم. سؤال 9:36. Okay. علق. Okay. لسه معلق. Okay. طيب, we can read it from here. If the average velocity in the main branch of a duct, okay, this duct in this problem, is 13.4 meter per second. So the average velocity in the duct is 13.4 meter per second. Calculate the duct height in units of centimeters. Obtain your results in 2 ways. Okay, showing all. مش مهم يعني, بس we need to calculate h in the duct. طيب, تعال ننتبه للدكت. عندنا بساي of the first stream, الستريم العلوي هو 4.35, وبساي في الستريم السفلي 2.03, وبساي في الستريم اللي هو بنقسم هنا it's 3.1. So if I tell you يعني calculate the volumetric flow rate, it's this psi minus this psi, صح? The volumetric flow rate coming from here, and then it will be divided between those two streams. So this is the part that will be divided here, and this is the part that will be divided here. Okay, this is one of your يعني question 962 is one of your homework questions. So it tells you to get the ratio of the volume that's the volumetric flow rate that's going to be divided upwards. It's easy. يعني we just say إنه this minus this is going to be the total volume flow rate, okay, of course per unit length يعني, or per unit width, and then this minus this is this segment only, and then 3.1 minus this is this segment only. And يعني إنه focus how إنه الستريم اللي هو على left side of the flow is higher. صح؟ لانه دائما الستريم على left side of the flow is higher than of the right side على right side of the flow. So we can get يعني انه ال ratio here. يعني this is not our question. But our question is how can we get the duct height? The duct height here. So focus on it. يعني برضو it's easy. Okay. From here to here, this is the division of the flow, and this is the flow here. Okay. So we need to get the duct height. It's يعني انه مش مهم ال divided here, division. ده بس مهم في question 962. H, this is H, and this is psi 1, and this is psi 2. Okay. So how can we get H? Now use the form of the continuity equation that we يعني محمد صلاح أول شيء mentioned it. You remember it? اللي هو إنه V V dot is equal to rho A V average. Yes. صح؟ V dot equal to rho A V average.
من دون الرو يا مهدي لأن
اوكي يا صح that was m dot. اوكي correct. تمام. this is it. طيب نحن حاليا عندنا اللي هو ال psi 1 minus psi 2. psi 1 minus psi 2 is the volumetric flow rate per unit width. صح؟ يعني بنضرب في الويدث. يعني انه psi وحدتها متر سكوير per second و v dot وحدتها متر كيوب per second. So we multiply by the width equal to الاريا هي عبارة عن ال height of the duct multiplied by the width and V average it's given. We don't have the width but we can يعني انه cleverly cancel it. بس خلاص يعني انه 4 point whatever ما بعرف كم 4 point something here 4.35 minus 2.03 4.35 minus 2.03. This is the volume flow rate per unit width. I already canceled the width equal to the duct height V average. One step solution. V average is given in the question. اللي هي عبارة عن 13.4. ف 13.4 خلاص يعني احنا هسه حلينا for H the duct height in centimeters. اوكي. ليه؟ لأنه هنا متر سكوير per second وهنا متر per second. فلما we divide them together we can get the duct height in meter بعدين نحوله على سنتيمتر. It will be if we do the division in calculator minus 2.03 over 13.4. It's going to be 17.3 centimeters. Okay. And for the homework question, يعني it's easy. You can solve it. What's the ratio? The ratio of the flow that's going upward. Okay. Let's call يعني بساي الأولى اللي فوق بساي 1. Okay. وبساي اللي تحت بساي 2. والdivision بساي let's call it بساي 3. فالراتيو حيكون psi 1 minus psi 3 which is the volume flow rate that goes upward and then psi 1 minus psi 2 which is the total volume flow rate and this is the ratio for your homework question. فيعني انه remember always انه الفائده من psi يا اما اطلع velocity يا اما اطلع volume flow rate بس ما في لا غير فائدتين velocities volume flow rates بس. خلاص بس يعني we finished now I think. في كمان اسئله بتحبوا نكمل ولا شفرت ولا عادي ولا فاهمين شنو بالضبط؟ بس هم أسئلة تحويط يعني I think ممكن ياخذوا وقت قليل. شنو رأيكم؟ نوقف؟ يا جماعة سامعين؟
براحتك براحتك.
عادي عادي عايز عادي.
طب اوكي تمام. الكويستشنز هنا موجودين اوكي اللي هم these questions okay okay. The continuity equation is also known as, what's the continuity equation? The conservation of mass, the conservation of energy, the conservation of momentum, Newton's second law, Cauchy's equation. The continuity equation is the conservation of mass, صح؟ زي ما أول شيء كان محمد صلاح قال. Conservation of mass, continuity equation. It's coming from the conservation of mass. طيب. Navier-Stokes equations, this is not يعني now, but يعني, you know, I think the professor told you in the beginning of the chapter, it's a result from Newton's second law, Navier-Stokes equation. So it is an equation that describes the flow, okay, F equal to ma, but now يعني, we add the viscous terms. This is the term that was missing in fluid mechanics. طيب which choice is the general differential equation form of the continuity equation for a control volume؟ يعني differential form, okay, for the continuity equation for a control volume. Which one? Which one is the general form? Not the compressible, not the incompressible, general form. This is it, the general form, differential one. This one, sorry, this one. Because this one is the integral form and this one also integral form. Okay, this one for the control surface only, and this one is, yani, this includes everything, but this is the integral form. I want the partial form, this is the partial form. Okay, and this is the general one. Here we eliminated partial rho by partial t. Okay, بس هنا this is the general one, which is D. طيب, which choice is the differential incompressible two-dimensional continuity equation in Cartesian coordinates? In Cartesian coordinates, when we have incompressible flow, so eliminate the density, and two-dimensional, so eliminate the z direction. So it is E.
Option E.
بالضبط. طيب, وديس يعني two are easy, يعني نفس اللي حلينا أول واحد 930. And we have a steady under which condition is the flow incompressible. So do partial u by partial y by partial x and partial v by partial y and partial omega by partial z should be equal to 0. If it is right, correct, then the flow is incompressible. We want to know what condition will make it incompressible. So arrange the equation and write the condition that will make it incompressible. هنا مثلا we have an expression for psi. What is u? U, we go to that table that I showed you, اللي هو بيقول انه how is the relation between psi and u, okay, for two-dimensional flow, and it will be partial psi by partial y. So partial psi by partial y, this one is 0, and this one is 2by and plus c, okay? So 2by plus c. And for v, it's the opposite, يعني انه partial psi by partial x, and don't forget the negative. So partial psi by partial x, and don't forget the negative. So it is going to be 2ax negative. 2ax negative. Okay, يعني careful, don't choose the positive one. لأنه الإيكويشن already فيه negative. وبس يعني these are the questions that are related to إنه part 1 of the chapter. Part 2 of the chapter about Navier-Stokes equations. These are them. Okay. Clear. مفهوم يعني كل شيء إن شاء الله.
الله يعطيك العافية.
يعطيك العافية مهدي.
تمام الله يعافيك. اوكي.
Thank you.
تمام.
Thank you.
اوكي في كمان يعني two questions الدكتور ما لحق يحلهم المرة الماضية اللي هم تاعين السلايدز، بيتكلموا عن نفس الأفكار نفس كل شيء بالضبط، يعني الدكتور لما يشرحهم بكرة إن شاء الله تكونوا فاهمين كل شيء، بس حيقول لك إنه derive بساي. سواء كان derive بساي مديك الفانكشن تاعت اليو صح؟ بتقوم تمشي على التيبل اللي هو موجود هناك. اوكي. أنا مش عارف التيبل موجود هنا ولا لا. I think هو ماخذ الدكتور البروفيسور الايكويشنز from the table. اوكي. وفي واحدة تاعت الكارتيزيان. I think he wrote it maybe here, yeah, for the Cartesian. So بس يعني إنه derive the equation for psi, and then he will tell you find the volume flow rate. So psi top minus psi bottom, that's the volume flow rate. And then again another question, but this يعني this one was a fully developed cavity flow. This one is open channel flow. Okay, this is an open channel flow. Same thing exactly. He will give you the u, then you derive the psi, and then you calculate the volume flow rate. Okay. وبعدين حتثبت آخر شيء إنه how is the volume flow rate correct by using the integral form that you took it in fluid mechanics. The integral form كيف بيكون for the velocity اللي هو بيكون كده sorry, or for the volume flow rate. No. Okay, integral form for the volume flow rate is the integration of v, okay, dA, صح? v dot dA. This is the integral form to calculate the volume flow rate. So you will إنه يعني تثبتها إنه psi minus psi is equal to v dot طبعا، بس إنه هنا حيكون إنه psi minus psi equal to the volume flow rate per unit width. Okay, don't forget it. Okay, maybe كمان يعني بعد ما الدكتور يحل كمان السؤالين نحن المرة الجاية نبدأ نحل سؤال كمان سريع عليهم على نفس الفكرة. Okay, وبعدين نكمل في part 2 of the chapter. These are the homework problems. تمام. بس اوكي. ان شاء الله ما اكون طولت عليكم، والسلام عليكم.
مع السلامة.
شكرا.
سلام.
Thank you. Thank you.
سلام.